So, this recorded lecture will talk about Ampere circuital law, which is actually the part 2 of your chapter 4. In the previous part, we have discussed about Biot-Savart law. And you would have seen that we've discussed both the magnitude and also the vectorial form, right? So it's a general way to calculate magnetic fields from any current distribution, right? We have considered a current carrying conductor, and then for example, this is a wire, and then we have taken a small element, and then we have taken a point, suppose x. So at this point x, what is the magnetic field that is being exhibited by this small element of dl of the current carrying conductor is what we have used in Biot-Savart law. But then if we see, this general way is not very much applied when symmetrical cases. So this is not very efficient method. Also because first of all, it is not telling us about the complete conductor. It is just telling us about the small element, right? So that is one limitation, that it is not giving us information or calculation of the magnetic field that is exhibited by the complete conductor. It is just telling us about the element of the small element of that conductor which is carrying current, and it is a very point to point calculation, right? So what I meant is we can only measure B at specific points. Okay, so you only measure B at specific point. You're only able to understand and calculate magnetic field at specific point due to small current element, and then you will have to integrate it. You have to add up all these small dls across that current carrying conductor to actually know the complete magnetic field calculation for that conductor, right? So we will have to do all this cumbersome lengthy calculation for the total field at that point. So we need some modification, right? And that modification, that means we need a solution to this, as in we need a calculation that helps us to calculate the complete magnetic field. Okay, so instead of at specific points, we want a complete magnetic field. So this can be obtained with the help of Ampere circuital law. So this limitation of Biot-Savart law is basically answered with the help of Ampere circuital law. We do not have to integrate a lot. We do not have to get into lengthier calculations. We can still be able to find the cumulative or net magnetic field for that complete conductor, not only its specific small elements of length. So all that we have to understand is Ampere law is going to involve a loop. So you know that Ampere is the SI unit of current, right? So that's why we have a closed loop in this law, which is called as Ampere's loop. And so we can consider magnetic field along the entire loop basically, and it simplifies the limitation and actually answers the limitation that we have had when we were discussing about Biot-Savart law. So let's just get into the discussion. We are basically considering this long wire in which the current is obviously flowing because the chapter specifically focuses on moving charges. And then you know that when you place your thumb on this current direction, you end up getting the direction of magnetic field using right hand thumb rule, right? So over here I might consider different points, for example point Q, point P, and you know that at point Q what will happen is your fingers will go inside, right? Which is why I'm using it this way, and at point P it will come outside, which is in this way, right? So what will happen is now we only have 2 points. So Biot-Savart law is generally explaining as a magnetic field, but what will happen if I give you 2 3 such points, R point, S point? So at that point of time also Ampere circuital law will help us, because it will consider all these points within one Ampere loop. So this Ampere loop is this blue color thing that I have drawn, and now it is easy for us to calculate. I will explain you how. We will just consider any small element on this loop, for example the small element dl, And then what will happen is magnetic field direction will also be through that small element dl itself. So what I meant is the statement of the law will tell us close line integral of b dot dl is equals to mu naught. This is permeability. Okay, don't confuse this with permittivity of chapter 1. This is permeability. Okay, so this is mu naught, that means free space permeability or air permeability, into I inside. So this is the statement of the law. So what is this explaining us? It is telling us that this is Ampere's loop, right? So this Ampere's loop is basically enclosing all these points, and this B and DL are what? They are they are dot products, sorry. Yeah. So in your chapter 4, grade 11, when something is a dot product, it will have a cos theta, right? So this will be B dl cos theta is equals to mu naught I, and this theta is where? This theta is basically between B and DL, right? That means this theta is between B and L basically. So I just told you that DL is in this and B is also in the same direction. So when when B and DL are in the same direction, the theta will be 0, and cos 0 is what? It is 1, right? So that simplifies the law basically. And it also tells us about, so this dl would be, because cos theta I'm just taking it off because it's anyways 1, right, which is cos 0. And instead of length I'm taking this as a circle, right? So we can take circumference of the circle, which is going to be b into 2 pi r, right, assuming that this loop has a radius of r, and this is mu naught I, and I is going to be the current that is enclosed within this Ampere's loop. So can you find the magnetic field? Yes, we can. Mu naught I by 2 pi r. So this is going to be the magnetic field. Okay, so we were not able to get such a final expression or total magnetic field basically with the help of Biot-Savart law. So Ampere circuital law solves that problem which was previously raised while discussing Biot-Savart law, and it is basically relating the circulation of magnetic field around this loop, basically this blue loop, right? It's explaining as a circulation of magnetic field around this loop, and this is relating it to what? It is telling that it is related to the I inside. Okay, so how I inside, I will explain you with the situation. So over here the expression tells us that it is relating the magnetic field around that loop to the net current passing through that surface enclosed by the loop. So it's a very powerful way of measuring the magnetic field, and rather than measuring it for small elements, right? So we get a bigger advantage over here. So let's get deeper into this. So what happens is, just let me take this off. So for example, you have a loop that is Ampere's loop, and within this you have different points. So that's where Biot-Savart can be used, but with a lot of calculation. So we don't want you to use a lot of calculation. We want you to just simplify it with the help of Ampere circuital law. So I'm just giving it name. This is I1, this is I2, and this is I3. This is I4, right? So how will we apply Ampere circuital law? Just get the basic statement. So it is B into DL, right? This is a dot product, which is equals to mu naught I inside. That's the basic statement. So when I'm using this statement, what I will be doing is I will understand that within this blue loop, how many currents are existing, right? So within this blue loop, this is outside, so this will not be considered at this point of time, right? So this was I2, this is I3, this is I1. So we will be using the statement of the law itself, and while using it, you can just help me out with this. This is going to be mu naught, and what all currents are inside will only be considered. Since I1 and I3 have the same direction, you can see that this direction is used for the current coming outside. So I1 is coming out, I3 is also coming out, so I'm adding them, but I2 is going inside, so I'm subtracting it. So this should tell me the complete scenario of the magnetic field, right? So it becomes easy with the help of Ampere circuital law is what we are trying to understand here. So now going inside the concept, we have to understand how will be the magnetic field due to hollow conducting wire. So I want you to understand first what are your ideas about how a hollow conducting wire would be. So what we are trying to understand is this is a wire basically, right? So for example, if this is one cross section of the wire, so what I'm telling is this is the symmetry of it, right? The axis that centrally divides it, and let me just assume that only at its surface the current is flowing, okay, because this is hollow in nature, so nothing flows inside is what I meant, right? So I'm just using two specific variables over here. So basically from the central axis, that means this one, to the surface I will use capital R, okay, and I will have three cases to analyze it. I think you will be able to relate it in the same way we have done this for Gauss law as well in chapter 1, where we were studying about how the electric field will be inside, outside, and on the surface of the conductor. In the same way we are discussing it for hollow conducting wire using Ampere circuital law. So when I'm talking about inside, so for that I also need to consider small r, right? So I'm just using any loop over here which is inside the wire because it's hollow. So now if I'm using this loop, this is not the right way of drawing it. Yeah, so when I'm considering this loop, at that point of time this is inside, right? So let me consider its radius as small r, okay? So this case will be r less than r is what I meant. So what will happen, you go to the statement that you have learned in your Ampere circuital law, which is BDL mu naught I inside, right? So what you can understand is over here, since there is nothing that is inside, it's all hollow, so it will give you the B inside of zero value, right? Because it's hollow. So now we can consider the next case, which is outside, right? So when I'm considering outside case, I will just change few things over here. So outside case will be what? It will be R greater than R, right? So which means instead of this, I will have to use R over here. So let me assume R over here. And when I do that, my Ampere loop will look like this, right? So when my Ampere loop will look like this is why R will be greater than capital R basically. Note down this clearly in your notes, otherwise you will be confused. And over here, the expression will turn out to be something that you have just written with me so far, that is mu naught I by 2 pi R. So this is for the outside case, and at the surface would be what? At the surface would be same again, it would be R is equals to R. So wherever you have R over here, you can exchange it with small r, right? So it will become mu naught I by 2 pi R. So that would be surface, this would be outside, and inside you know that it's hollow, so it would be 0. So these are the three cases we have to extensively discuss: 1, 2, and 3. So now I will just write them in a simpler format. So B inside is 0, B outside is mu naught I by 2 pi small r. B surface will be mu naught I by 2 pi capital R. These are the three cases we have discussed. Now we will be asked about a B versus R graph. That means B is on y axis, as you can see, right? R will be on x axis, right? So how will you draw this? You can see that I'm just drawing this wire for your reference. Let's assume the wire is like this, right? So just for your understanding, what we are telling is this is inside, right? So this would replicate this case, this one to be specific, and then you have a B outside case, right? A B outside case would be exactly following up here, and a B at surface case would exactly follow up at its surface, right? So this is how we graphically represent. And if you would see it properly, what happens is you'll be able to see that I will draw this again, right? This is the wire that we have taken. So at the very center you must be knowing that it is 0, so your graph should also show 0, right? Because this is B is equals to 0 inside. What will happen if you go outside? Can you see this expression? What is the relation between B and R? It is an inverse relation, right? So that means R is decreasing when B is increasing, right? So we will also go in the same way. We will have to go till the outside, which will start from here, right? So this is outside, and then at outside from here this graph will start, it will decrease. So this is what B inversely proportional to R means, right? And even if I go to surface also, I will have the similar relationship, because here also if you see this, you will be ending up with this itself, like this. But this graph is about B and R, not about B and capital R. It's about B and small r, right? So be conscious with that. So over here also, this is still inside, correct? To be specific, if I draw it, this is till inside. So till inside it's 0, and from outside what will happen? It will decrease in the format of B inversely proportional to R. So this is how your graph will look like. Okay, in exam there might be a chance that they give you just a minute, they might end up giving you the graph directly like this in an assertion just to verify it. This is R, this is B. They might end up giving you a graph of this format. Is this correct or not for a hollow conducting wire? Yes, it is correct, because this is B inverse to R, this is B inverse to R, and this is exactly B is equals to 0. These three conditions are reflecting what you have learned over here, right? So this is a graphical representation of B versus R. Remember that this is small r, and small r was what we have taken for our Ampere's loop, the radius of Ampere's loop. Okay, so this is a very important graph. Until now you would have seen the magnetic field due to a hollow conducting wire, right? And we have drawn a graph as well. Now we will see magnetic field due to solid wire. Solid wire does not means that this is a wire and it has been filled with solid. No, that is a wrong idea. The correct idea would be, for example, when you go to the lab and you just peel the wire with the help of a cutter, right? When you peel the lab, sorry, I mean when you peel the wire, you will see that there are so many copper windings in it, right? So that is what we generally call solid wire in physics. Okay, so it's not a wire that is filled with material, but it's just that there are so many multiple wires inside within a wire, which we will be able to visibly see when we peel it, right? So I hope this clears the doubt. And due to a solid wire, what we see is these are all infinite wires, right? From our frame of reference, they're very long. So this is the outlining of a wire, we can see, right? So I'm just making it infinite, so I'm just not making any boundaries on top and bottom. So this is the axis the central axis of symmetry, and you know the same r I will use from the central symmetry to the surface, capital R, and your ampere loop radius will become small r, right? And there are multiple wires within it. I'm just drawing that with yellow, right? Multiple copper winding wires, just like how you peel the wire and you will see. So the concept remains the same. Here also we will have to measure the magnetic field inside, outside, and also at the surface. So let's start with the easy cases first. So outside the wire, let us understand. So that would be r greater than r, right? So if I consider r point over here, what will happen? You will have to eventually consider a ampere loop. So when you consider this ampere loop at that point of time, what will happen? You will end up getting the same what you have got before this as well, that is mu naught I by 2 pi r. Now for surface also, you know that r will be equals to r. So you can just make a minor change that will also be similar, right? So these two, for hollow wire and for solid wire, solid and hollow infinite wires, these expressions will remain the same. Something that will change is the inside expression. You know, inside expression is small r less than capital R basically. So for this, the expression is going to be b mu naught I 2 pi r square r, 2 pi r square r. Write this properly in your notes because this is capital R and this is small r. Okay, so if I realize for inside case why the expression is changing, because inside this one solid wire there are multiple wires. So when there are multiple populated wires, the area inside is the inside volume is being occupied by multiple wires. We need help of J. So J is current density, so which is why this expression changes a bit than the usual expression of what you have studied in a hollow wire, obviously, because hollow wire does not have those multiple wires inside it, right? So can you analyze how B and R is changing over here? Let me, yeah. So over here they have an inverse relation, right? Over here they have a direct relation. So this will help us to draw B versus R graph for solid wire. You know, we have also drawn the same graph for hollow wire as well. So I will collect all the expressions for solid wire. So the inside expression, which is going to be B is equals to mu naught I by 2 pi r square r. For outside, it remains the same like hollow wire expression only. That is mu naught I by 2 pi r. At the surface also, it remains the same like hollow wire expression itself. That is mu naught I. The only thing is small r will be exchanged with capital R because it's surface, right? So we are drawing a graph between B versus R like the previous one, right? And just to repeat it again, this small r is going to be what? It is the, so if you see, I'm just drawing the wire over here and there are these multiple wires inside, right? So following the same explanation, can you see how B relation is from here and how B relation is from here? So I can see that outside the wire it is inverse, right? So till here it is inside and this all area is outside, right? So let's draw for outside. It will remain the same like the previous graph itself because B and R are inversely proportionals. And then inside it is not like how it was previously, right? In the previous we have seen that B inside was 0 for hollow wire, but here it's not 0. Here inside is actually directly proportional. So for directly proportional, you know, B increases, R increases, B decreases, R decreases, right? So this would be the graph. Okay, so this is direct proportionality. Basically what I'm trying to make it is B directly proportional to R, right? So let's just accumulate all the expressions we have studied so far. We have studied for hollow wire magnetic field, and we have studied for solid wire. Yeah. So let's collect these expressions. You will help me out with this. And for solid wire, we have three cases, right? Inside, outside, and surface. So the inside case, what we have studied for the hollow wire, what was that? The inside case is going to be 0, obviously, but here it changes, right? It is right, and the next is going to be the outside case. And for outside case, I think correct me if I'm wrong, it's going to be mu naught I by 2 pi r. Here also the outside case will be the same. Let's discuss the last one, which is for the surface, and that is also the same itself. Yes, so you have to understand all these expressions are collected at one place now for our ease, right? So the expressions, if you see, we have drawn B versus R graph, right? So B versus R, where R was what? R was the radius of the Ampere's loop. Okay, so you can see that this is inverse, this is inverse, which is why outside the expression in both the graphs is the same, but inside changes because over here it's directly proportional and over here it's 0. Okay, so this is the discussion for solid wire. Sorry, this should be hollow and solid wire, right? And we have discussed about magnetic fields. You can take this in your notes. All these expressions should be there with you, and we've also drawn these two graphs for both the analysis that we have discussed so far. Now the next case is of a solenoid. You would have seen a solenoid in your grade 10 also in the chapter magnetic effects of electric current, right? So there what happens is you have a core basically, right? Let's assume yellow, I'm drawing my core with yellow, and on this core only you're going to wrap up the wire, right? Let's assume this is how we wrap the wire. So can you see now how a person is going to wrap the wire? Basically he or she is going to be the observer, right? So his frame of reference is going to matter a lot. Okay, is he wiring it from the right end or is it wiring from the left end? What is the person's preference? The frame of reference will differ. I'm considering one for your understanding. Suppose if this is how it is, simplifying the diagram even more, right? This is enough. So if this is how I have wounded the wire on that core material basically to make it a solenoid, you know its number of turns, right, that are coiled around a basic, you can just maybe like your laptop charger or your phone charger, you can just try to coil it across your water bottle or any plastic bottle, right? So that plastic bottle will behave like a core, and your number of turns that you provide will start behaving like a solenoid, right? So when you do that, I want you to understand about current directions over here. So what I meant is, from one frame of reference that I have taken in this video, can you tell me on top what is happening and on bottom what is happening? So on top you'll be able to observe that current is coming outside. So for outside we have this is how we denote outside, right? And on the bottom you will see that it is going inside, so this is how I'm denoting it. So in a solenoid, a student should understand that the wire on top portion and the wire on the bottom portion, the current directions will go opposite, right? Even if there is a student who is following up this video right now, listening to it, wants to take it to the other way. For example, I started coiling it from the left end, sorry, right end, you want to coil it from the left end, you'll obtain the same results. Probably your this will go on top and this will go on bottom, but eventually the result, what I'm trying to say is, the wire on the top and the wire on the bottom, in terms of current directions, will be opposite, is what is means. Okay. Yeah, so since now we've understood and discussed about the directions of current on top and bottom of the solenoid coil, right? So what will be its total magnetic field, or B net? So for this also we will be using, it is actually an application of Ampere circuital law only, and this ends up at mu naught Ni. So I is going to be the current, in that coiling around the core, right? N would be number of turns, right? And mu naught, it is permeability, right? So this is a constant anyways, and sometimes instead of number of turns they will just give you small n basically. So what they mean is, it is number of turns per unit length. So that means this n is equals to number of turns n per unit length, right? So you can also substitute this in this formula and rewrite it like B is equals to mu naught N I by L. That is also fine. You can use this or else this, both are fine. Okay, so what we mean is, when you take a core and you coil it, what are we seeing is, at the edges, can you observe, these are the outside edges, right? The one that I've labeled with pink. So over here you can see that the magnetic field will reduce, and throughout the core it is constant, right? So throughout the core is this yellow portion, it is constant, and outside, if you see, it will decrease or reduce basically, right? So we have a graph that represents this equation. We will draw this graph now. So we will draw a B versus L graph basically. Okay. B versus L graph will give us a lot of information about, I think previously I have used capital L, right? So you can just check in the video once again, right? This is length of the solenoid. So what I meant is, if I take a solenoid and I wrap it around, so just drawing the graph from this reference only, this is B versus L graph, right? So um, so throughout the core it stays constant, so this portion it will remain constant. But if you see, these are the edges, right? So let's go with the edges, it will reduce. So this is how your graph will look like. I'm going to erase the unnecessary portion that I've drawn for your understanding. And this is how your final graph will look like. So what we mean is, it will remain constant throughout the core portion, which is this yellow portion that I've drawn here also. And if you see the edges, which is this edge, it is reducing. This edge, it is reducing, right? So sometimes they do ask us how much does it reduce. So you can always tell that throughout the core, that means throughout this portion, it is how much. B is equals to mu naught Ni, right? And over here it might reduce to half of its value, so it can be mu naught Ni by 2 at beyond edges basically. So this is a B versus L graph for a solenoid. And now I hope you're able to understand the Ampere circuital law. I will try to sum this up. I'm just wrapping it up, what you have learned in this part with me. So we started the discussion with limitation of Biot-Savart law. It's just measuring the magnetic field for an element of the current carrying conductor from a point, right? So we don't have the complete information or calculation of magnetic field as such by Biot-Savart law. In order to do that, I'm not saying it's impossible, but in order to do that, you will have to do repetitive integration, which is tough. So that is why we end up choosing Ampere circuital law. And Ampere circuital law is helping us. It's the line integral of BdL, which is equals to mu naught I inside. So mu naught, I hope you know, this is permeability of the air, right? It's a constant. And I inside is what we are trying to measure. This is the line integral. So that means throughout the conductor, this will measure the complete magnetic field across the L. So this is a cross product is from where we started the discussion, right? So that means B and DL are in the same position, which is why it is cos 0 is 1, right? So after that, we have applied this on what? We have applied this on a wire that is conducting but is hollow nature for inside, outside, and surface case, and we have considered a solid wire again for inside, outside, and surface case, and for both of them we have drawn graph, and the third application was for a solenoid. For all these three we have ended up measuring the total B, and we have understood that all these wires offer a very good symmetry also. I want you to understand, right? For hollow wire also, when I was drawing it, I have drawn a central axis, and the same I have done for a solid wire also. Let it be multiple wires like I'm drawing with red right now, it will still have a central axis. And again, if I consider the solenoid as well, so you have a core, and this is how you wound the wire. Okay, you can start from here or you can start from here as well, your choice is fine, but on the top to the bottom the current directions will vary is what we meant, and this is also having a good central axis. So what we are trying to say is, when you have good symmetry, it is a good option to use Ampere circuital law when you try to have a choice with Biot-Savart law, because Biot-Savart law involves a lot of integration repetitively, it being used at small element of the conductor, not the full conductor as such directly. Not impossible, but directly we can't apply, right? So here we can apply it directly because it is talking about mu naught I inside. If you are mistaking this and writing it just I, it would be wrong. This is I inside, that means inside the loop. Whose loop is this? Ampere's loop. It's an imaginary loop which we are trying to create, and then we are trying to calculate the net magnetic field across that. So this is it. This is finishing your Ampere circuital law explanation of this chapter.